Sorry guys, I had issues with the camera setup, but I think we're pretty much set up now. So the bomb actually was released out in the morning today. I'll just go over the different parts and the different items that are part of the bomb for the toolhead. And at any time, please, if you have any questions, just let me know in the chat, and I'll keep an eye on that and come back to answer the questions as and when I see them. So essentially the tool head is 6 printed parts, or 7 printed parts actually. These two actually fit together. So this is the main extruder body for the tool head. The extruder body essentially has the Z probe built into it. It houses an optical switch that is like the normal optical switch and stop that you get, the cheap one, and it sits in the extruder body using these two button head screws. These are I think M3 by 8 button head screws. So that's the first part. Then the second part essentially is the motor mount, which is this one here, and it essentially houses the motor and the drive gear. The motor sits in the back like this. Now, before we go around to assembling this, let me just go over and mention what are the heat set inserts and where do they actually go in. So on the motor mount, the heat set inserts go in 1, 2, 3, 4, and then there's one on the top, 5. So it essentially is all M3 heat set inserts, 5 on the motor mount, and then 1, 2, and 3 on the extruder body. So I already have these prepared, but when you're assembling it, just use a file to clean out some of the zits that actually come in when you because of the Z-hop, because these two surfaces are going to mate like these, like this. So you do not want any spacing or anything to be out of alignment. In addition to the heat set inserts on the motor mount, there is also an M3 hex nut that goes in here. So you need to prepare this beforehand. I also have the optical switch installed, as I mentioned. Now, the next step essentially is to assemble the top extruder body. The way the top extruder body essentially goes together is you have the BMG gear, and this is the idler gear. I think I'm missing the bearings. Just give me a second. Just give me a second, let me get the bearings out. There we go. So we essentially have a standard BMG assembly, pretty much the same thing that goes in for goes into the Clockwork 1, Clockwork 2 dual gear BMG. So just get the bearing and press this in. So that is where the motor mount main drive gear goes. And then in addition to this, the NEMA 17, the NEMA 14 motor essentially goes in here, and what we will be using is two M3x8 socket heads to mount the motor in. Make sure the rotation of the drive gear is without any skipping. So that is the preparation for the motor mount. This motor mount is done. In the extruder body, we will essentially just keep these on the side. We'll come back to these when we need them. So now on the extruder body, we essentially can take the drive gear, or the out of the two BMG drive gears, we'll take the smaller one, the one with the what do you call it, the set screw, and it let's find the correct Allen key. Yep. So it mounts in the reverse orientation to, I think, the clockwork. So just keep it a bit loose because we need to finalize where it sits based on the alignment with the hole for the filament. So there's this hole in the filament and then it goes like this. So we'll just also install the other bearing. And what I normally like to do is to just take a piece of filament just to make sure that the alignment is fine. I'll just take a piece of filament, feed it through, just to cut it at an angle. So if you see, the filament actually gets feeded in here, and the extruder body and the main drive gear sit in like the main motor mount, they sit in like they actually get coupled together like this. So now that we actually have this, we also need to install an Hall effect sensor on the front of the tool head. So what that will essentially allow us to do is to know if the tool head is attached to the carriage or not. So there's a magnet on the carriage that will trigger the Hall effect sensor, detecting if the tool is correctly installed or not. So I have this Hall effect sensor that I've already soldered in the 3D leads into. This is the same Hall effect sensor that is used in the ERCF. I do not remember the number of the part number, but you can actually look up the BOM. But this is the same Hall effect sensor, and if you look into the ERCF manual, it will actually give you the pinout as to how you need to attach the wires in to this Hall effect sensor. So we are essentially going to mount this Hall effect sensor with the angled side facing out. So I'll just do a 90-degree bend on the Hall effect sensor pins, and then I'll just feed the wires in. Now if you see, this actually is going to sit in this slot here. So the angled side or the beveled side, not the angled one, the beveled side essentially is going to sit in the front. What I normally like to do is to actually kind of just use a dab of super glue to hold it in place. So I have this standard super glue that I use for a lot of things. I'll just put in a small drop and just let it sit there. So the wire for the Hall effect sensor comes in addition to the optical sensor. Both of these wires actually come out from the top. You just make sure that the Hall effect sensor is essentially sitting flush with the body. So that is primarily what you need to do on the extruder body in terms of the installation of the different components. So now we essentially have the motor mount, and we also have the extruder body that is done. So what we can do is we can just make sure that the wires are coming in here, and we can just attach them together. Let me just make sure the wires are being fed correctly in here. Just wanted to see if everything is getting is going fine in terms of the way I'm explaining it. If there's any suggestions on how to better illustrate the assembly process, please let me know, and I'll be glad to adjust. I think we're just kind of sitting a bit high on the gear. Okay, I know what the issue is. So the issue essentially is this part of the drive gear, which needs to be flush. I think there is not enough space in the back. This is like a new component that came in, so let me just get another one that already has is better done in terms of this. Just give me a second here. Yeah, so here we are. I'll just use this one. All of these are not, all of these are like the cheap gear, BMG gears. I think the cheap China copies. So, and they work fine for me. I haven't had any issues in those terms with PLA or anything. So I've just been using these on pretty much all my builds. I just get the bearing off. For a second here. Sorry. Okay, so I'll now if you see, this is flush. The other one essentially had this bevel, or this was actually protruding out. So I don't know if it's something to do with this specific main gear, because this is something like an aftermarket one that I bought. This is the one that came with the kit, so I think we should be fine in there. Yeah, so now we are, if you look at it, we're sitting nicely flush, and I think we should be able to press these two together much more easily than we were able to do that on the other one. Yeah, so now there's no spacing or anything, there's no gap. So all that we need to do is to make sure that the drive gear essentially is good. Okay, I think this might be the bad one, because I had one of these drive gears that was not correct. Yeah, just give me a second. I'll grab another one from the other packet. Just give me a second here. Yep. Okay, I have way too many of these that I need to. And a bunch of these are kind of stripped. Sorry about this, guys. I just don't want to kind of get into a situation where the drive gear essentially is not working correctly. That would just make it impossible for me to actually get the extruder working. So, yeah, almost there. Just give me a second here. Okay, I think we have this sorted out. Sorry about this, guys. Okay, so I don't know why it is getting stuck here. Yep. Sorry guys, these came out of the old build, so I don't know if there's any issue with these. Okay, I think we're good now. So, okay, so let me just get this back in. Sorry about this. Just make sure this is rotating freely, and then we take the other bearing, we can get it on the top, and yep, I think we are aligned, pretty much aligned with the whole thing. We just loosen it one bit, feed in the filament, and then just tighten it. Okay, so good. Just tighten this properly so that we don't have any filament slippage. And now we can move on to the next part, which essentially is tying this together. So to tie this together, we essentially need, one will be an M3 by 25 up top. Then there will be an M3 by 30 that goes in at the bottom. Might just be a bit, it might take a bit of force to actually kind of get this in, because the heatsink insert might actually have come up a bit, but I have not seen it create any issues per se. So I think it's either M3 by 30 or M3 by 35. Let me just try the 35 first, and then we'll see if that works. If not, then we will put in the, if it's longer, we'll put in the M3 by 30 in there. So let me just get the electric screwdriver. Yeah. Okay, so we have the 35 that actually worked in there. Let's just make sure that the gear and the motor is rotating freely. Just do that by hand. Okay, so now this is done. Now the next one is the idler in here. So idler is pretty simple. You have these two needle bearings, and you have an M3 by 20 pin. What I like to do is to kind of just lube these bearings just a tiny bit. Just use normal grease and then put them into the idler gear, feed in the M3x20 pin, and so just make sure that it rotates freely, and then the okay, I think the hole is a bit undersized on this, so what I normally do is kind of just heat up just the end of it using a butane lighter, and just push it in. I just need some more. There you go. Okay, so we have the idler assembled as well. It goes in here, and then there's an M3x40 screw that goes in from this side and then screws into the what do you call it, M3 hex nut that we had on that. So what I can do is that is it. So that is the basic assembly. We'll come to the front with the rail and then the kinematic coupling in a bit. So that is the first part. The second one is the Hotend body. So let me just kind of put these away. So I will have to figure out how to take care of the other gears that are in there. Thank you for the comment, Doinger 1987. Really appreciate it. Thank you guys. Really appreciate you guys following around, and it's just been a pet project for me in that sense. Not something that I do full time. It's just like something to blow up the steam. That essentially is what this is. But it has turned out pretty well, I must say. I did not expect it to actually turn out this well, and for me to be able to actually deliver on what I wanted to, what I set out to design. Because there were a lot of things that were in the air when I actually started up. But I'm glad to see it actually coming together. Okay, so now this is the interesting part. So essentially, we're done with the extruder assembly. The bottom part essentially is the one that houses the hot end, and then it also houses the Z probe, the integrated Z probe. So the Z probe is kind of based on a tap-like system, wherein the nozzle essentially is used to probe the bed. But instead of using a linear rail, we essentially are using a LM5UU bearing that along with some spacers and stuff. So the way that we actually put it together is essentially there's this part which is the hot end mount, and then the one that actually travels up and down on the linear rail, on the linear bearing. So what we need to do, essentially the first thing that we need to do is to put in a 5 mm 5 by 25 M5, or this is a 5 mm rod with or a 5 mm by 25 double pin. So what I will do it is I'll just, there's this notch or a hole that is there, if you guys can see it in there. I think I need to redesign this particular part of the extruder body, of the Hotend body, but it works fine as is. It is just there to kind of hold the rod, and I haven't had any issues with it, so I haven't really gotten around to redesigning it. So all I do is actually just kind of put this pin through just a little bit, and then just apply a small dab of super glue to just keep it in place. Then we have this LM5 UU bearing. It's like a normal linear bearing that is there. So let's kind of just use some grease to lube it up so that it travels nicely. It's like the normal lube that you use on a 3D printer. And then just make sure that we wipe out the axis of it. So this bearing is supposed to ride up and down on this 5 mm shaft. So if you see this is how it rides. Now we install the bearing here on this side, and if you see, it has a smooth motion that can be used for the Z probe. But we essentially need to triangulate the motion so that it does not actually kind of wobble to left or right. So to do that, we use two spacers. These are like M3 spacers. So we have 4 of them. Where is the 4th one? Right here. So we have 4 of them. So if you guys look at it, it's a 10 mm spacer. Let me just confirm it's 10 mm. Way too many magnets all around. Okay. No, sorry, it's 5 mm. It's not 10 mm. It's 5 mm. So this is like 6 mm OD and 5 mm height spacer with a 3 mm hole in the middle. So what we're going to be doing is we will install them on this part here, and we'll install the second one in this hole here. So now these 2 holes, they essentially are going to be used for magnets. Similarly, the counterpart holes for these 2 spacers here are this and this, and then the magnet counterparts are this and this. The holes are press fit, but they do take a bit of effort to get in. So I might, for the magnets to go in, I normally use a plier or something like that to actually just put them in. So I'll just take one of these, I'll take a plier, and just push this in. Like this. I'll push the second one in also. Don't use too much force, it's just to get them in there. Just make sure that you're not clog the hole for the M3. So just push it down so that they essentially are well set. You should have a very fluid motion. It should not catch onto anything on the Hotend body. Now, when you look at when the part first gets printed, so there might be some extra piece of plastic or zits or anything like that might actually be sticking out. So I normally take a file, a flat file like this, and just go over the whole the cavity, if you will call it, where the movement will occur. And then I do the same thing on this part as well. So I take out especially the rounding corners and everything. I normally will just file them out just to make sure that there is nothing that actually catches on, and the motion should be very fluid. That is important for the Z probe to actually work. So if you actually look at it, there's absolutely no friction. It is just sitting in the area that it needs to sit in. Let me just plug the charger cable in. Sorry. And so that is the first thing. That is what needs to be done. So essentially, just make sure that there is no friction between these two parts. They should just move really smooth. Now we need to install the magnets. So this essentially is standard 6x3 Voron magnets that everyone uses. So we have 4 magnets in here. So we will need to press the first one in right here. Then the second one, I'll just make sure that I have the same, excuse me a second, I'll get another magnet. Just make sure that I have the same polarity. So I'll just take this, push it here. Just push this in. Now I can just take 2 magnets with the opposing polarity in here and just press them in. Just want to make sure that they're completely pressed. So what I can normally just use is I can take something like a mallet, and along with the mallet I normally take like a, like that. Yep, I take a piece of 5 mm rod, just light tap all across the board, just to make sure everything is sitting the way it's supposed to sit. You can use anything. I'm not hitting it really hard. I'm just giving it a light tap just to make sure everything is flush. Now you'll see the movement has changed to something different. It is not an unconstrained movement. It actually just pushes back, and you have that opposing force in there. So this is a very important part of the whole assembly process, which took me a while to actually figure out how to get right, and have repeatable results with the Z probe. So if there are any questions around this, I can actually answer them, because if you do not get this right, the Z probe accuracy is going to take a hit. It will not be repeatable. It's very important to get this part right. So if there are any questions, please put them in the chat, and I'll answer them. There is one last step that is left to get this assembly completed. That requires two M3 by 20 pins. So this is one M3 by 20 pin, and then this is the second M3 by 20 pin. They need to go in like this. Now, what you will see sometimes is, because of the fact that every printer is going to be a bit different, and this requires very smooth motion. So the two spacers, this should be completely aligned with this one, so that the pin just kind of goes in straight, and there's no friction when this piece moves up and down. Same needs to happen on this side as well. But what I've seen sometimes is that depending on the printer and depending on what the print actually looks like, you might actually get a little bit of variation in the alignment. So to handle that, it took me a while to actually figure out how to get this to be good. Is that I essentially can use a soldering iron to kind of just heat this up slightly, just enough so that it actually has the plastic around it is malleable, and this spacer can move a bit to the side, making sure that this pin actually kind of goes in straight. So right now, if you look at this pin actually goes in straight, but this pin essentially has issues with the alignment. So if I was to push it in, what this would do is it would actually kind of start locking up the smooth movement of we need a movement like this, even with both the pins in there. So that is what we'll do. We essentially will just use the soldering iron. So I have this heated up at the lowest setting. I will just use this. Let me just let it heat up just for a couple more seconds. What I'm doing is I'm just pressing it slightly, just so that it can actually transfer some heat to the spacer. It's an aluminum spacer, heats up really fast. Now that it's heated up, all that we do essentially is just push this pin back in and just move this up a couple of times. So you'll see. So now we actually have both of these pins in the going in straight. So when they actually go in straight, you essentially have a very fluid motion with the magnets pulling the piece back in. So that is one of the most important pieces of the assembly. To get this right is very, very important, because this essentially is going to decide what kind of accuracy you can get out of the Z probe, and the repeatability you get across tools. So now that this is done, any questions around this or anything, if you have, just please put it in chat, and I'll be glad to answer them. So just make sure that you actually kind of have this. Looks good. Now what we can do is, now that this is done, we essentially can mount the hot end. The hot end needs to, it's going to be different for each and every hot end. I'm not going to mount it just right now, but I have this, I have the Triangle Lab TD6 CHC hot end with an integrated nozzle. So that allows me to actually kind of do the mounting in two parts, with the heat sink being mounted like this, and just the heat sink, and then the ceramic body actually kind of goes in from the bottom. But if you have something like a Dragon, you'll have to mount it all together. Now this, so Mike, this is all ABS. You can use ASA as well. I don't think there should be any issues with the ASA. It's just a different, it has very similar properties to what ABS is. I don't think you need carbon fiber or anything like that for any of these parts. They work just fine with ABS, because there's no force that actually is applying on any of these parts. The reason there's no force is because pretty much all the force essentially is taken by the metal parts. So be it the linear rails that are there, we'll come to this in just a second, or even on the tools carriage, all of the contact points while locking and unlocking, they essentially are metal to metal. There is very little force that actually gets exerted on plastic. So, and that is one of the reasons I can actually push the tool changer to be sub 2 second tool change with very fast locking and unlocking. That is because of the fact that everything is metal on metal in that sense. The plastic essentially is just being used as a shell to hold the metal pins together. So similar in here, pretty much everything I have is ABS printed on the 2.4. So you can just use ABS or ASA, and there should not be any issues at all. So Mike is asking about the fact that he's having problems with printing without support. So Mike, I only have the 2.4 that essentially is doing the ABS right now, and on that I have had no issues printing this the pieces with without supports or with the inbuilt supports. The only two pieces that actually needed support in my case were the XY, the redesigned XY joints on the rebuild that I did, because that had space for the sliders to go in even when actually moving to X to the Extreme X. So I really don't have any experience with MK4 or the enclosure that you might be using. You might actually want to use something like an air circulation system within the enclosure that kind of drives the temperature up. See, ABS needs at least 48, 50, 55 degree ambient temperature to not curl up or to not split. The other advice I can give you is to actually use something like a different blend of ABS that essentially is easier printed in printers like MK4. Eason used to come out with a pretty good ABS Plus, but my experience with ABS Plus over the last couple of years has been that the strength on that particular filament is just not there. It splits very easily under load. So I would not advise you to use something like that, that particular filament, but you can always look at something more premium, a filament that essentially is an ABS blend that is easier to print. So I hope that helps, but at slicer settings, I don't think there's anything in the slicer settings that you can do if your ABS actually is curling up or if it actually is not staying put. So, so moving on, yeah, ABS Plus is Eason ABS Plus. It's easy to print within an enclosure, but lately the strength on that particular filament has just not been there. If I was to kind of give you an example, just give me a second, I'll show you what I mean when I say about the filament strength. So you look at the 2.4 right there. All of the black pieces that are there, they are from the original build, and they are Eason ABS Plus. This was printed on a Creality Ender 3 that I had with an enclosure. And at that point of time, it actually printed just fine. But after that, I started using some of the other filaments, blends of Eason ABS Plus, and it was just really, really bad in terms of strength. So just give me a second. Let me just kind of put the gimbal on charging as well, without making it fall. Just give me a second here. Okay, sorry. Sorry guys, just give me a second. I'm just getting the whole thing settled up again. Sorry about that. Okay, so let me see. Let me just get back to this. So where were we? Okay, so now that this is assembled, what we need to do next essentially is install the Hotend. So as I was saying that based on what Hotend you're using, you'll have to either install. There will be different ways to install it. You would need a Hotend with the 4 top mounting screws to actually work with this particular version of the Hotend body. So you can just install it with the 4 screws going in here, and then there's wire routing for the heater and the thermistor from here. So I'll just show you the wire routing so that you guys have an idea as to how to route the wires. So if you look at this, here is the wire routing that essentially you can just route the wires out of the back side like this. So just make sure that you are essentially using thin wires. So these are like 20 gauge wires, PTFE wires, and then these are the normal thermistor wires that come in. I think this is like 24 gauge, I believe. So I'm not going to mount the extruder on the Hotend right now, because it will depend on what Hotend you're using, but it will just mount to these 4 holes in here, and then the PTFE tube, depending on what Hotend you're using, will go through the center like this. We'll come to a part about the PTFE tube because there's a spring that actually needs to be installed on this PTFE tube when we're putting these 2 pieces together. But just to show you guys the operation of the whole nozzle probe. So if you actually look at this, that is the optical switch that we had. Now this will actually go in like this. So these 2 holes are for the 2 M3 what do you call it, M3 dowel pins, and this one is for the M5 dowel pin. So you essentially they'll just go in like this very easily. And then if you'll see that there's a flag, there's a small flag that actually protrudes out of the Hotend mount. That is what is used to trigger this optical switch, based on when the nozzle strikes the bed. So you go back up and you should have a movement like this. This sound is something that is going to be really, really important for you to actually hear and confirm, because this is going to tell you that your recoil movement is actually working fine for the nozzle probe. So that is how the whole thing is going to be put together. So the final thing essentially is going to be that you actually put the PTFE tube in like this, and in the PTFE tube you essentially are going to use a small spring. It can be just give me a second, let me just get the spring. So it has to be a very thin spring, something like this. So this is like a 0.5 mm wire. What you need to do is you usually need to, this was like a 15 mm or 30 mm long spring. What I need is I need 4 coils out of it. So this is the length of the spring that I need. and this will essentially go in. The PTFE tube will pass through this, and it will go in like this. What this does is it actually gives you the recoil movement that is needed when the filament is loaded. So if you'll actually look at this, so you will need that in order to be able to have this Z probe working when the filament is loaded. That is very important. Without the spring, it works sometimes, it does not work sometimes. With the spring, it actually works very, very reliably. So that is one thing that you need to keep in mind when you're assembling this. Now let's come to the other part, which essentially is the part about the linear rails and the kinematic coupling. So before we actually put these two together, we need to do the linear rail installation on the two parts. So essentially, let's take this part first, which is the lower body. So this is the MGN 12 linear rail that has been cut to size using the guide that is part of the repo. Now, one side of the rail, which essentially I think is 35 mm in length, or thereabouts. Yeah, 35 mm in length. So one side essentially has just like small angles cut in, or it is. So the way that I cut it is I use an angle grinder to cut the two holes out, or just the part of the rail with the two holes. Let me just show you how you actually should be aligning the guide. Just give me a second. Let me just find the guide right here. If I can find it. Okay, I can't seem to find it. But when you are essentially using the guide, please use it from the back. So just put those two prongs on the guide into the back, mark it in there. Do not put it in the front, because if you put it in the front, it can move back and forth. On the back, it will actually stay put and allow you to mark accurately. So now that this is there, we need to prepare it to work with the tool locking mechanism. So what we need essentially is we need two bearings. These are MR63ZZ bearings, and they will essentially sit in these holes on the front. The back holes are going to be used to bolt this to the plastic piece. The front holes essentially are going to be used as the locking mechanism. So these MR63ZZ bearings, what we are going to do is, I'm just going to take a small dab of super glue and just put some of it in here into the hole, and then I will just press fit the bearing in there. And what I will just do is I'll just use the mallet to push it all the way in. Just to make sure that it is sitting flush. Just use this, something like this. Now that gives me is a way to have this M3/16 pin go in and be held in place. So that is how you prepare the tool locking side of the linear rail. You just need to make sure that this pin is rotating freely. And the super glue essentially is just going to make sure that it actually, the bearing sits tightly in this hole and it is not falling out. And if you feel that it is not rotating freely, just hold it with, if you give it a few rounds, you'll loosen everything up. It will start working the way it's supposed to work. Okay, so we'll do the same thing for the other one as well. Again, the other rail. This is the front. I normally mark the front with the these two side cuts, and just use a small bit of super glue. Push it in. Just make sure it's sitting flush. It's level. Just use the M3/16 pin. Make sure it rotates properly, and then we are done. So that is how you prepare these two linear rail locking bodies. Now to attach them to the plastic pieces. It's not very difficult. So just keep in mind the way the two pieces have been designed essentially is that you should be able to access this hole to put in the M3 by I think 12 socket head. Even after assembling this, you should be able to adjust that. So the way that these two pieces have been designed is that from the top, for the top rail, the M3/12 socket head goes from the top. For the bottom piece, it goes from the bottom. So if you look at, there's a hole in here that the M3/16, M3/12 socket head will go through. And there's a corresponding hole on the top as well, which essentially is used to align the hex nut or the square nut that actually goes into this particular cavity with the, align all the three things together: the hex, the M3 square nut, the hole for the linear rail, and then also the M3/12 socket that is coming up. So what it helps us with is that it helps us do the, it makes it easy for us to actually kind of fasten them together. So the way that I normally just put it in is just push it in. And if you notice, there is adjustment. So these linear rails can actually slide in and out. This is to allow us to actually adjust the length of the linear rail based on the sizing of the hole distance, because I've seen that different linear rails, MGN12 rails, have slightly different spacing between the two holes. And then it also allows us to kind of adjust how much of the linear rail actually sticks out, because this is what determines the force that is needed to lock and unlock the tool. The more it sticks out, the less force is needed. But if it sticks out a lot beyond a certain point, then there is absolutely no locking that is there, because it just slides in. The slider just goes through it. If it is pushed in too much, the amount of force that is required to actually lock is pretty high, and the printer actually skips steps. So that is why the adjustment is there, so that you actually have the ability to just have that adjustment, just be able to control how much force is needed. And to be clear, you don't need a lot of force. You don't need a lot of force on the printer to actually lock the tool. What is keeping the tool head in place is a combination of the locking mechanism and also the, yes, put it here. So it's a combination of the locking mechanism, which is the slider that actually goes in, and the kinematic coupling that goes into the dowel pins, because that essentially on the tool head, on the tool carriage, because those three cylinders that actually go into in between the dowel pins, they keep the tool locked, while the locking system essentially is just providing enough force to make sure that it actually does not slide off. So you don't need a lot of force in the in this particular system to be able to lock or unlock a tool. Just to give you an idea, I essentially am using 1.2 amp on X and Y motors without any skipped steps or anything that is happening while locking or unlocking the tools, and it actually works perfectly fine. So that was just something that I wanted to kind of throw out because as you guys are building it, you'll actually see that the normal tendency is to actually make sure that it is very tightly locked, but that is not required. And doing that is counterproductive, because it will essentially lead to skip steps on the printer, and it will also lead to a lot of and it can also lead to the plastic it being subjected to some force that can lead to the fasteners or the linear rail actually is coming out because of the fact that it is moving in and out. So that was something I wanted to throw out there. So let's get back to this. Just give me a second here. Okay. So now that this is there, what we need to figure out is we just need to we essentially need to make sure that the hole is through. You just need to prepare the hole, because there are two sacrificial layers that are used for bridging the holes while printing. So so now that we essentially have this in place, we will use this M3 by 12, and I'm going to use a square M3 nut. So the square M3 nut kind of just goes into that square hole. Just push it in a bit. And then I'll use this Allen key just to align the hole. I'll just use this Allen key to align the hex nut or the square nut, the linear rail, and just make sure that it actually comes out from this side and it is not falling out. Then I can just take this M3 by 16, M3 by 12 socket head and just move this in. So just need to adjust a couple of small mm so that the fastener actually can just picks up. Okay, so now we are attached. So I'll show you how the adjustment works. So you just loosen it up a bit. You'll see you can actually slide it in, and you can slide it out. So this gives you the adjustment that is needed to adjust the amount of force that is required to engage the locking mechanism. So right now I'll just leave it a bit loose, but still fasten. So that is that particular piece is done. We need to do the same thing on this piece as well. So again, the same stuff, we just put it in the hole, just push it in. Again, we have this M3x12, and then we have our square nut. So mechanical fluff, particular reason I chose the Trident over the 2.4. Yes, so the 2.4 essentially is a flying gantry, and you cannot load the tools onto the back of the gantry itself, because it's going to get too heavy, and then the gantry itself is what is being lifted up and down. So all of that weight gets added to the gantry. There has to be a different approach that has to be taken for the 2.4 tool changer. There are multiple approaches that are being developed. For example, VCore actually has the, just give me a second here, let me see what happened here. Sorry about that. Okay, so yeah, so VCore actually is doing the stealth burner, the tap changer and the tap changer light, which essentially parks the tools at the very top. And then it also is a mechanical tool changer. There is no wires or anything on the X carriage. So that is definitely a viable solution on the 2.4. The only caveat that I see with that particular tool changer essentially is the fact that the tools are being stored up top. So every time you need to make a tool change, you have to kind of go up, pick up the tool, do all of that cleanup magic, and then you come down and start the print again from where you left. The time that it actually takes for that movement is one, it is going to be a bit longer than what you would actually have the tools for just at the same level as the gantry. In addition, the other thing also is that when you're doing the movement from the top and then coming down to print again, all of the cleaning that you do on the nozzle with maybe either a purge bucket or a wiper brush or anything like that, you'll still have some oozing that actually happens as you move down. That cannot be. There are other ways to mitigate it, but that essentially becomes a huge issue as if you want to print without a prime tower or anything like that. So, and the fact that it actually takes time for you to go back up, get the tool and come back down. Any time that is taken there essentially is going to be exponentially multiplied when you actually have multiple tool changes happening in the course of a print. So just give me a second, let me just let the dog out, and I'll be back. Sorry about that. You can do it at the bottom as well, but it's the same thing. As you move up in the print, you have to come down and you have to do all of the Z movement. So that essentially is time consuming, and then any time that is spent on tool changing is going to be multiplied multiple times, depending on the number of tool changes that are there in the course of a print. So I have certain other ideas on how to adapt this particular mechanism onto a 2.4, but that is essentially a topic of another discussion. So let's finish up on the tool assembly. Yeah, Caramel Zappa, I agree. The tap changer is a wonderful solution that VCore came up with. The only issue that I have with that particular solution is the time it takes for a tool change. It's in my experience, anything above 4 to 5 seconds for a tool change is something that is going to add so much time to your print over a course of a long print. So just to give you an example, so this is what I printed on a couple of days back on the tool changer, and this essentially took, I think, like this whole thing took like maybe about 6.5 or 7 hours to actually print up. And this had like 650 plus tool changes across the whole print. Now that was with a tool change time of, I think, about 4 seconds or something like that, 4.5 seconds. Now you double that up to about 8 or 9 seconds or 10 seconds. And you can see how the time actually kind of just goes up. So any time that you can shave off out of a tool change is time that you spend and that you save while in the actual course of print. So apart from the fact that the tool change time on the tap changer is a bit longer than what I would like, it's an amazing solution. VCore actually came up with an amazing solution, and it is something that is original to him. See, the one that I have is inspired by Prusa XL, so I cannot actually claim the the genesis of the idea of something like this. This is just an open source version of what the Prusa XL tool changer mechanism is. But the idea that VCore actually came up with, it's his own baby, and he did an amazing job with that. So anyways, we're getting off topic here. So this one, again, the same thing. You essentially have a square nut that actually goes into the square hole. You use the Allen key to kind of just align them up, and then I essentially just can push this in and lock this in. So same level of adjustment here as well. Now to put these two together, you essentially are going to use that spring, put in the PTFE tube, push the PTFE tube through to the hot end. Now this will of course be cut to length depending on what hot end you have. And then there are 4 screws that actually kind of hold them together. 1, 2, 3, and 4. So these two are M3 by 6. So let me just get these. I'm really bad with the Allen keys. They just keep flying off my hands all the time. Okay, and then this one here. Then there's an M3 by 12 that actually goes in here. So let's get the M3 by 12 here. There's an access hole from the bottom. You put the M3 socket at here and you just bolt it in. While you're doing this, just make sure that you actually have this movement. This movement should not get blocked by the over tightening of the screws. And on this side, there's a socket head that actually goes in here. This is M3 by 16. So we have this 16 here. Again, the access hole. Take it. We just reel this in. So again, so if you see, this is what I was talking about when I mentioned that this should not get restricted. So this is the sound that you're looking at. This is something that should always be there, the spring recoiling back, because this tells you that you have a good Z Pro functionality that you can actually use reliably. So that essentially is the assembly. Now for the fans, there is a 3010 axle fan that goes to this side. Sorry. This is from the earlier build, so might need to strip off some of the heat shrink. Just do that quickly here. Okay, so we have this going in like this. And then this goes up to the top. And then we have the so right now the only Hotend that is supported is going to be, so it can support any Hotend actually has those 4 top mounting holes like this. So that means the Rapido, that means the Dragon, that means the Revo, all of those are supported. In terms of the extruder, I have built this around essentially what I had in terms of the LGX, in terms of the the dual drive gear extruder. This part or this face needs to stay as is, exactly the same in terms of the linear rail placement, the kinematic coupling placement, and all of that's it. As long as this actually stays the same, this particular piece remains static, you can put anything in the back. But keep in mind that that will also affect how many tools you can actually put in onto the back extrusion. Because one of the reasons this actually looks like this, which is not very pretty, is primarily the fact that I wanted it to actually have the smallest footprint possible. So just give me a second. The dog is barking. He needs to come back in. Just give me a second here. So this essentially is, I think, about 50 mm or something like that when I find it. Yeah, this is like 47 mm in terms of its width. Now you take 47 mm and then you also need to have 12 to 14 mm of space to move. What that essentially gives me is about 60 mm of space between each tool. Now, if this was something like a stealth burner or any other tool head, unless until you can modify it or design it to actually be slimmer than what it currently is. I think stealth burner or stealth burner mini, I think is about 60 mm or 70 mm, something around there. So you're losing space on the back, and the tool density actually then goes down. So coming back to the point around the different extruders, you can design it to actually use anything that you want as long as this front plate remains the same. As soon as the files actually are available, I think the community is also maker stuff. There's work that is going on the CAD, on the Fusion assembly and all of that stuff. See, I have no experience in Fusion apart from just viewing and hiding panels and making sure I can actually understand what is going on within a particular design. I cannot design in Fusion. My brain does not work that way, just to be very, very honest. Tinkercad essentially is more like combining bits and pieces and kind of making one thing look like the other. That is how my brain works, and that is what I've designed this whole thing on. Fusion assembly is going to come out, and I think that will give you a better way to identify how you actually put other extruders and other hot ends on this. In terms of hot ends, as I mentioned, as long as it is top mounted, this design actually supports this. So I don't think hot end is that big an issue. The extruders, obviously, you need to have other extruders available as well for you to work with. But right now, the only one that is working in this tool head essentially is the dual gear standard from Clockwork and everywhere. So I hope that answers the question in terms of what support are we looking at. So just to finish this off, this is where the 40-20 fan goes out. It sits like this. And then there is this parts cooling duct that I designed, which actually looks really ugly. But this is the best I could come with given my limited skills in making something contoured in Tinkercad. So the parts cooling duct essentially kind of just sits in like this. It for the moment it actually is glued onto the fan, and then it sits in here to push air. It is pretty effective in terms of the design that is there, but I'm pretty sure it can be improved tremendously. And there's no flow analysis or anything that I've done. I've just practical some tests that I might have done with my hand, feeling how much air it actually is pushing in, and that was the criteria I used to finalize what duct to use. So again, this is one area that can definitely be improved upon by people who are much more adept than me on the Fusion side or on the CAD side. So the 40-20 fan actually sits in here. This is where the back extrusion is going to come in. So once this is assembled, the back extrusion is going to fit in between the motor and the 40-20 fan. So it's very important. That is one of the reasons they're actually sitting a bit low. So that essentially is what the assembly of the tool head looks like, and how you actually have the linear rails and stuff working for the tool locking mechanism. There is another Hall effect sensor that actually is going to go in here. So that is to detect the docking and undocking. So it will actually go in like this. So again, it will have to be glued in. Okay, and then the NeoPixel LED is going to go in here, and I just use some hot glue to actually kind of put it in place, paste it in place. You can obviously come with a better solution, but that is what I do right now. Just put some hot glue on top of on the back and just paste it here. So the final piece essentially is the mounting for the EBB36 board, because all of these wires, they actually come to this side. If you see this, they're coming from here. Then the NeoPixel or the Hall effect sensor is going to come into the back. So this is how the EBB36 module is located. So this is the top encoder or the filament encoder. I might just redesign this whole thing, so I will not go into details on how this actually works, because I'm not really happy with the design of this. But for now, I'm actually just using it as a PTFE connector holder. So you can just plug this in, the PTFE connector here. It uses that 10 mm connector with the 4 mm internal diameter PTFE tube. So that now that we have this, it sits in like this. And the EBB 36 mount sits on the top. And then there are M3 by 25 fasteners socket heads that attach it to the main body. So now that this is done, this EBB 36 mount has two hex screws. One is pressed in the front here, and the other one is pressed in the back here. So let me just get an EBB 36 board and I'll show you how it actually gets mounted. So that's an EBB 36 board. So it gets mounted here. So I'll be using M3 by 8. I think sorry, M3 by 6 on this side. Then M3 by, I think M3 by 12 is what I do here, this side. So it has to go in the back. And then all the wires, they terminate onto this side of the tool. They will terminate onto this side of the tool, and they can actually be plugged into the EBB 36. So that essentially is pretty much the whole assembly that needs to be done for a tool head. Anything else that, any questions that you might have on assembling the tool head? Yes, we missed one very important thing, which essentially is the kinematic mounts, the kinematic coupling mounts. So there are multiple options being explored for the kinematic coupling mounts. The one that I'm going with right now essentially is to use M5 button heads and a 6x3 magnet glued on top of that. So to glue it, I'm actually using something like the Loctite HVHT glue, which essentially is a metal to metal glue. And it is pretty solid once it actually sits in. But I'm also looking at the acorn nuts. So let me show you what the acorn nut actually looks like in the ones that I've got. Just give me a second here. And so you can actually see what the difference might be between the two of them. It will require a change on the tool changing system or the tool changing. So I assembled this tool head earlier, which is a completely assembled tool head. So let me just kind of use this as an example. Just keep the one that we're assembling on the side. And the dock is assembled on this as well. And I'll come to the dock in a bit. But so if you see the kinematic joints here, what I have is essentially it's an M5 hex screw sitting like this. On top of it, there is an M5 button head. And on top of that, what we have is a 6x3 magnet glued into the center. So that's the M5 hex, then the M5 button head, and then a 6x3 magnet coupled on the glued onto the top of it. So that is what I'm using as the kinematic joint at this point of time. The other solution essentially is to use something like a acorn nut. This is what an M5 acorn nut actually looks like. So there would again be a hex, M5 hex sitting in here, and you would use something like a M5 set screw to mount the acorn nut on top of this. It will definitely require some changes to push the hex nut down into the body so that the total height of the acorn nut that actually sticks out will be in line with what we have here. Because right now, if you look at it, it essentially is sticking out a lot more. So that will be a change that will need to be made. Also, the tool locking body will need to be adjusted for the width of this acorn nut, which I think is 7.1 or 7.2. This essentially is 6 mm. So right now, the distance between the two dowel pins, the two parallel dowel pins, essentially is I think 6.15 or something like that, because I don't need to have a lot of margin in there. So I'll have to adjust that for the new acorn nut. But I think this should also work in that scenario with this. But right now I'm actually sticking to it because I have the tool body mounted and working, and I do not want to actually kind of change it. But for anyone who is doing a new build, I think this solution will also work instead of something like this that I'm doing in here. So that essentially is where the 3 kinematic couplings actually goes. This actually is like 3 hex screws pushed into the body with M5 by 8 button heads screwed in, and then I'm gluing in a M5 6 by 3 magnet on top using the Loctite HPHT high strength glue, which is a metal to metal glue. So I hope that answers the question around the kinematic couplings, and also how you're assembling the linear rails, and why have the linear rails been chosen, because the choice behind the linear rails essentially is because of the fact that the distance between the 2 holes is just ideal for us to actually work with the with the tool locking mechanism, and also the hole that is there allows me to press fit a bearing in there, and so I do not need to drill over anything or anything like that. All I have to do is just cut this rail to length. So that was the reason behind using MGN12. If there's any other alternative that people can actually think of, obviously that would be a better solution, but this is what I could come up with, and it has been working out fine for me. So so that's the tool body. Now let's look at the dock for a second, and the magnets that actually need to go. So while we're looking at the magnets in here, this is the assembled tool head that I did earlier today. So these two are M4 by 16 dowel pins, so just like these, that are just pushed into the holes. They essentially are used to hold the tool onto the dock so it does not fall out. So this is the dock, and then we also have magnets. So we have these. This is like a 6 by 6 magnet. These are 6 by 3 magnets. These are 8 by 5, I think, and these are again 6 by 3. And this is, so these are 8 by 3 and these are 8 by 5, these two. This is a 6 by 6 that essentially goes into the tool head right here. The reason I've not glued it down is because it needs some adjustment when you actually mount it on the dock. So this will be glued down once this is installed. These three are 6 by 3 normal magnets. These two again are 6 by 3, and these are 8 by 5. And this is a 4 by 4 magnet which lines up with this Hall effect sensor, and that allows me to detect if the tool has been picked up or dropped off, and that is used for the intelligent error detection and the error recovery. So this is how the Hotend is installed. So I have this Hotend that is installed on the tool head, and this is where the so if you can look at this, so if you hear that sound, that is the Z probe working, and the spring pushing back. So on the dock, the other thing that needs to be done is to install these two heat set inserts into these holes. These are M4 heatset inserts, just like these. They will be installed in here. And then for the final piece on the dock, you need 2 pieces of 95 mm long M4 rods that go in here, and these are used by the tool locking mechanism to pull the slider left and right. To add rigidity to the whole thing, we also need 75 mm M3 rods that will go in here. Might just need to be pushed in a bit, but they will essentially sit like this. So they will sit in, one will go in here and the other one will go in here. The reason they're not installed is they will be installed once this has been installed onto the extrusion, because while you are setting up or adjusting the height of the tool in relation to the carriage, you will be removing these 2 pins and then manually locking and unlocking the tool to the carriage. So all of these pins, all of these rods get installed once the final installation has been done on the extrusion process. So I will make another video on how to actually install this tool onto and the dock onto the extrusion. But I hope that answers the questions around what goes into the dock and how the tool head is assembled. Any other questions that I can actually help answer around the tool changer mechanism or the tool head assembly, anything like that, I'll be glad to answer. Just to be remind everyone, the BOM for or the bill of material for all the 3 pieces, the tool locking mechanism, the tool head and the dock, that is updated and it is available on the GitHub repo. I will be adding more details onto the GitHub repo as I find some time. Yes, just this here. So yeah, so that's it. I don't have anything else that I can kind of assemble right now. Any questions, anything that I can actually help answer? Just please throw that into the chat and I'll be happy to answer. Cool. So if there are no questions, you can always ask the questions on Slack, on the Discord channel, and I'll be glad to answer them. If there are no other questions, I think we can end the stream. And Mike, any suggestions to a Premiere ABS blend to replace Eason ABS Plus? I have no idea. Others who are in the same geographical region as you would be better able to answer that question, because I have been using, I've not used Eason for a long time now. So what I've now done essentially is that I have started using a local Indian brand called Dream Polymers. I use the pure ABS from them, and it actually has been working out pretty well. The strength on that particular brand is pretty good, but it's only available in India. Just to be clear. and it's pretty economical for what for the quality that it has. So you'll have to kind of ask around as to what a good ABS blend is. I'm not sure about Prusa Mint. If I would presume that Prusa Mint will be good. So okay, so the wire loom. We haven't covered that today, fun days, but just to give you an answer, essentially 20 gauge wire. Um, I think I have two 20 gauge wires for each polarity. So I am attaching two strands in parallel, bringing them up to the top. So let me just kind of show you essentially what I mean. Give me a second here. Let me just see if you can just say hi to the dogs. That is one. That is the other one. I have two more dogs that are sitting, that are sleeping downstairs. So yeah, four in total. So so if you look here, essentially you'll see these are the so I have two sets of power wires coming in here. So these are like 24 volts coming into these Vagos, or the Chagos, if you can call them Chinese Vagos. Same goes on this side as well. These are coming off two different power supplies. So depending on, I'm going to use these two tools, are going to use these two, because the same power supply that is driving these two tools is also driving all the electronics. And then there's a separate power supply that essentially is supplying power to this 24 volt. And these three tools that actually come in here, they are going to be using the power from this side. Apart from that, everything else is being driven from the EBB36 board, which is being connected using USB. So I have this power, I have this wire loom right here. So I can just kind of turn it around a bit, see more clearly. So this is like three. This is the filament. This is just rigid umbilical, and what this came out of was those drain cleaning, the drain catcher pipes that you get on Amazon. So this is just that rigid part from that. This is like a nylon braided steel within there, and the two wires for the tool head, the two power wires, 24 volt, they essentially are coming in from within through the hollow tube that is there, and the USB cable essentially is coming in here. I do not use CAN for my personal reasons. I just don't. I have not had good experience with CAN. It's too flunky for me. Could be the cables that I was using. Could be the other things that I was using. So I just decided to use USB, and I'm using a USB powered hub down here at the side right there, that essentially is being driven by the Pi, and then all of the 5 tools have the USB cables terminating into that USB hub, and then they are coming in from the side. So if I can just use the wiring, show you the wiring scenario here. So I have the wires traveling like this up here. Same on this side. Just turn this light around here so that we have some better light here for us to actually look at. So, and then this is the filament addition that I did. The spools are gonna move up and down a bit so that I can actually have a spool in the middle, and this is gonna be the heated storage for the spools. So yeah, so that that essentially is it. Just to kind of show you how the kinematic coupling actually works. So let me just see. So if you see, this is unlocked. I can just, let me just see. It's difficult to do it with a single hand. So it sits like this, and then just lock it in. So that is what I'm using for the kinematic coupling, and it actually works just fine. So I hope that answers the questions around the wire loom. Any other questions that I can actually help answer? Sure, I'm glad to help. So just don't look at the mess around my table. That's not something I want you guys to see. So that's the 2.4. So the idea that I have around the 2.4 essentially is that instead of the tools being attached to the back, we can come up with this add-on that essentially bolts onto this particular side of the frame with the tools sitting in the front, and then it rides up and down as the gantry moves. So the tools are always available for the carriage to kind of just pick up instead of going up, picking it up and coming back down. So by extending this out using bolt-on frames, the original frame will remain the same. You're just bolting on one extrusion on top, on the front. What that does is that actually kind of preserves the build size, because the tools actually will sit out, and then these panels will just sit on the new front, which essentially is going to be the 20 part of the 40-20 extrusion that actually sits like this here. So that's the idea that I have. I think it should be able to work. Will require a couple of lead screws or belts to actually have that tool gantry move up and down along with the main gantry, but should be doable without any loss of build space, and just have things to be more like a bolt-on solution rather than actually being something that you have to make modifications to the main machine on. So if you don't like it, you can just take it off and go back to whatever the old machine was. So that's the idea that I have. I think it should work based on what I've thought about. But that is something that will be next for me to actually work on once I have this whole system working. So that's what that's it, guys. Anything else that I can answer, please let me know on Discord, and I'll be glad to answer. So thank you guys for sticking around and kind of helping me make this video. because I hope the recording of this video actually is helpful to others who want to assemble the tool head and the dock. It's fun answering the questions and stuff. I'll be available on Discord if you guys have any other questions. Thank you so much. I'll end the stream now if there are no other questions. Sounds good. Thank you guys. Take care. Merry Christmas again. And I'll catch you guys on Discord. Thank you.